I don't remember what happened, but it had, like, we were experimenting, you were in the library, and it just shows your, whatever your symbol is. It was that stand back, I'm trying science, and then like it has these little speechy rays coming out of it when you talk. It was funny. Very funny.
There. The hair is supposed to be like this all day, and then it kept falling out, so I left it, and now I have it back.
All right.
Alright, so Bob can select one or more, but you want to select one.
Yep.
It's only one.
Yeah, but you can still select more than one.
No.
Don't. It's not. Don't.
If you can select more than one, surely that means there's more than one right
I had
answer.
the wrong one still checked. I didn't answer, I just checked the wrong one.
Starting at x equals 3. The local and global maximum, and moving to the right of the slope. To the right, the slope is 0 and decreasing.
Is that right?
Mm-hmm.
Okay.
The what? 0 and
0 and decreasing to infinity. Because when you start here and you start going to the right,
Oh.
it's like, oh no, it's going down and decreasing, no, forever.
It's true.
Terrifying. Oh my god. As you approach x equals 3 from the left, the derivative is down.
as you approach that, the derivative is positive and I can put 2 of them. Increasing to infinity?
How would be increasing?
Okay.
You're approaching 3.
Which one are you on? 11?
I think so. 10.
10? I think it's 10 or 11. You pointed out as a doesn't have a right answer.
So we'll just discuss.
Well, yeah, if you don't mind taking a look at it. And,
As you approach
They're the
x
exact
from the
same
left.
question, they're just in the opposite direction.
yeah, isn't like
This was
they always
asking
go
what
from
the
left,
derivative is. The other
Yeah.
one is slope.
but really the idea is that slope and the derivative is the same.
So, yeah, I guess.
So it's decreasing to 0.
It's positive
So that means
and
it would
increasing
be
to.
this?
Oh no, no, because you said it's the same slope, right?
Yeah.
So it should be positive and increasing to 0.
No, it should be positive and decreasing. I think that's
Positive and
Oh, decreasing to 0, yeah.
decreasing to 0.
So it is there.
This is 10. Okay.
Yeah, 10's right.
Okay.
Alright, so this one would be,
Starting at x equals 3, moving from the left to right.
it should be negative and
So we're going down again. So it should be.
Hey, Luke.
Hey, how's it going?
Good. Thanks for coming.
Yeah, thanks for having me.
We're just debating question 10 and 11 here. Did you say it was 11 doesn't have a right answer?
Oh yeah, number 11.
Number
I
11.
was like, this stuff.
I think too.
Okay. All right. So
So what do we do?
okay. Gonna try something. Just be patient.
Oh, that's
While
a good idea, RJ.
while I try something.
RJ's smart sometimes and actually has
Oh,
good ideas.
thanks.
Okay. As you can tell, there's lots of complimentary stuff going on here. Okay. I've shared my screen. Hey, what does it look?
Oh, it's pretty. No,
Okay.
Well, it's not pretty, but like.
You know,
when you
yeah.
see
It's
it.
it's prettier than I am. Is that what you're saying?
No.
Okay.
Can I make it like full screen though, or is it just gonna?
I don't know. How does it look?
It's like mostly there, but not.
Oh, okay.
It's like that on RJ's too, so I think.
Okay, so you're just seeing kind of a chunk of it.
No, I see all
You
of
can
it.
see
It's
the
just
entire
smaller.
thing, it's just, yeah.
It's not full
Okay,
screen
all
on
right.
this. Like,
Okay, so we're talking about higher order derivatives, and when we're talking about higher order derivatives, instead of talking about the rate of change of a function, we're actually talking about, anybody care to guess, complete that sentence?
Instantaneous.
It's actually the rate of change of the rate of change of a function. So here we go. Number 11, starting at x equals 3, moving from left to right, the derivative is,
So are you just talking about we're going right from x equals 3?
yes, that's what it should really say,
That's
right?
kind of opposite.
Yeah, starting from x equals 3 and going from to the right.
Negative and
It's negative and decreasing to,
it should be increasing to infinity. Isn't it?
yeah, you know what? It should be negative and decreasing to negative infinity is what it should say.
But it shouldn't be
No, yeah.
because the slope's getting bigger.
The slope is getting bigger in magnitude, but it's
Sure.
decreasing. Yeah.
Okay.
So decreasing to negative infinity.
So
Does that make-
negative and decreasing to the infinity is the answer.
Yeah, I think so. Luke, does that make sense?
Yeah, that makes sense.
Okay. Yes, and I think I've got.
No, it's wrong.
Uh-oh.
You've selected too many options. Whoa!
Okay,
Selected one.
maybe I need to
One
fix
is
that.
too many.
Maybe I need to fix that.
Yeah.
Okay. All right.
So we'll just go on.
Okay. I will fix that, and we'll just proceed with. Good. No more pretty screens. You got your ugly old math teacher back. Okay. So we're going to do higher order derivatives, and basically we're taking the second derivative. So if we have a function f of x, took the derivative right away, and it's x squared, what's the first derivative?
2x? Is that what we're talking about?
So the first derivative is 2x. Okay. I'm going to ask you, Luke, what do you think the second derivative is?
2?
Yes. So really, all you do is take the derivative of the derivative. And makes sense, right?
Yes.
And you symbolize it. You symbolize the second derivative with the double prime. You can also do exactly. There's also like the Leibniz notation, which is d squared x over dx squared. But you'll probably recognize it. And then after that, usually it's like a little. It's the number of the derivative in brackets after that. So what's the third derivative of our function, RJ?
Sorry? 0?
0, that's right. Yeah. Okay. So the derivative tells us the rate of change of the function. And we'll actually get in a little more in depth about the derivative and the second derivative and what it's telling us about the function later. But the second derivative tells us the rate of change of the rate of change. So that's pretty important for physics, like if you had a distance-time relationship. The first derivative would tell you the velocity. And guess what the second derivative would tell you?
Acceleration.
The second derivative would be acceleration. Yeah. Perfect.
We're really good high five.
So here we go. Let's do a really big example. So there's our relationship. Y equals x to the exponent 4 plus 3x squared minus 5 square root x. One thing I always dislike are radical signs when
So
you're
we should
doing.
do 5x.
So yes, let's change that to 5x to the exponent 1/2. Okay. So everybody, we'll take like, I don't know, 30 seconds, do that derivative. And then I want RJ to hold up his answer.
We'll be able to read it? Just kidding.
No, nobody will be able to read it.
It looks like a negotiable.
Okay.
Okay, I'll tell you things to do.
I can see a lot of. Whoa.
More than that, but I can see it.
Hey. I think that's right. Luke, do you agree?
Yep.
All right.
Is that negative half?
Yes, that's right. Yeah, there's a negative 1/2 there. Good. Okay. While I'm writing this on the board, I want you guys to find the second derivative. There we go. And we'll go back to the. Oh, that's Luke. There. Ugly math teacher.
Just click on your face and we'll go away.
All right.
Easy.
Good. Okay. Okay.
So that's squared.
12x squared. That's right.
Plus 5 over 4.
Plus 5 over 4.
X to the exponent negative 3.
X to the exponent negative 3 O. Halves.
Okay.
Correct.
I was like, oh.
Yeah, that's right. Okay. How was that? Pretty easy? Okay. So not much to this. You're just taking the derivative of the derivative. It has an implication. It actually tells you if the slope is increasing or if the slope is decreasing. Okay? And we call it concave up and concave down. But for today, we're just like taking the derivative of the derivative. Crazy. Okay. So, hey, gang, what rule do we use? Right. Quotient rule, yes.
I don't know what this was.
So, bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared.
Derivative of the bottom first, right? Yeah.
Bottom time, bottom,
QP.
bottom times the derivative of the top. No.
Bottom.
Bottom times the derivative of the top. Uh-oh.
No, derivative of the bottom times the top, isn't it?
No, it's bottom times derivative of top
Well, I'm
Yeah.
just gonna check.
times derivative of
Brain's
top
not.
times bottom, or top times
Don't you know?
derivative of bottom, all over bottom.
Oh yeah,
squared.
Q times P prime minus P times Q prime.
All right. So we're going to take the derivative and then we'll simplify it a little bit. And Bob will be our uncle.
Really? Actually, boss. How hard do you want to stick with?
Oh, why don't you, somebody tell it to me sort of in unsimplified form and we'll simplify it a little bit and then we'll take the second derivative. Okay. Anybody volunteer? Meg.
Okay. 2x times 5
So
minus
bottom times the derivative of the top, subtract.
5x minus 3 times 2.
Times 2.
Divided by 3.
Divided by 2x squared. Very good. Is that what you got, Luke?
Yep.
Perfect. Okay, let's simplify this a little bit before we take the second derivative. So 10x minus 10x plus 6 all over.
Ryan, since you're ready, come to the office, please.
Hey,
Hey,
look how simple this gets.
this is so beautiful. 6 divided by 4x squared.
And we can actually do that again a little simpler.
So 3 over 2. X squared.
3 over 2x squared. Very good. Now we can do the second derivative.
0 over, is it? No,
No.
sorry. Brain
We can
fart.
we can use the quotient rule on this.
Oh,
Yeah. Or we could use this, we could also treat it like 3 has x to the exponent negative 2. And we could actually use the power rule.
what do you think?
Well, I think, some of us should use the quotient rule, some of us should use the power rule and see that it all works out the same. But what do you say? The power rule is actually easier at this point.
I call power rule.
Power rule,
I'll do it.
RJ is doing quotient.
Right on the
Okay.
buzzer.
Luke, what are you going to do? Power or quotient?
I'll do quotient.
All right, perfect.
That's a big one too.
Yeah, guys are doing quotient rule. Girls are doing power. It's girl power day, right?
Is it?
No, I don't think
Okay,
so. Is there such a thing?
probably. I don't remember the product rule. It's probably that.
Well, you don't need the product rule, just the power rule.
Well, I don't remember the power rule.
You do.
Oh,
The
yeah.
power rule.
Okay, that's
No.
what that is. Okay. So there was like the song that I didn't remember.
Oh, no, you don't need to remember a song.
Okay, that's good.
Bottom times derivative at the top, so
So that-
the derivative of 3 is 0. Right?
Yeah.
So that's really
I was debating whether it was 1 or 0 because I kept thinking, oh, you bring that down, it becomes exponent 0. Anything to exponent 0 is 1, yeah.
Oh, okay. It's
But-
actually, it's actually x to the exponent 0. Right?
Alright.
And then the 0 comes down and multiplies out to 0. Okay. Meg, what did you get?
Hold up.
Nobody's confident yet.
No, like
I've already done that. Alright.
the brain's just not wrapping around this exponent. Would it be -1 or -3? -1. Or am I just not?
Oh,
It would be negative
Would it be
3
-3?
because negative 2 minus 1 is not negative 2. You owe $200. You're taking another $100 back. You do not magically only owe $100. It doesn't work that way.
okay. So
Get bankruptcy.
Megan's going to tell us the power rule answer. Luke's going to tell us if the quotient rule matches up.
I got -3x.
Might screw it up, but
Well, Megan's saying she got like -3 x to the exponent negative
3.
3. RJ, what did you get?
I got negative 12x.
yeah, I got that. And then
Mm-hmm.
over 4x power 4.
So
Oh, right, I forgot to do over.
Luke, you're right.
I
And
knew that was too simple.
this is actually going to simplify to the exact
Negative
same
4.
thing.
So I did do it right.
Yeah.
That's very good feeling.
Yeah.
So it's good.
So -12 divided by 4 is -3, and x divided by x to the exponent 4 is
Oh,
x to the exponent -3.
yeah, you gotta do it divided by.
Perfect.
Yeah,
It's
so
important.
Yeah, and it doesn't matter what form you leave it in, like -3 over x cubed, is nicer. Okay. Everybody's good so far? One more, dealing with all of the ugliness of like doing the product rule twice. Or just once. Okay. Chain rule. Yeah. Derivative of the outside function with respect to the inside function times the derivative of the inside function.
I don't think I was here the day you guys did this lesson. Like, you explained to me and it's going for example.
I did my homework for my break.
Okay. Well, I gotta
So-
do it then. But I don't do it.
We started just pretending like leaving this inner part alone.
It's
Yeah,
times, right?
that's
It's
what I remember.
multiplied.
Multiplied by, so
Alright, yeah.
derivative of the outside times derivative of the inside. And so there's the derivative of the outside function with respect to the inside function. That's the formal way of saying it. Now we have to take the derivative of the inside function. So 12x squared, oops, plus 6x. If I could spell it right, be away to the races. Okay, so there's our first derivative. We are going to look around for things we could factor out and simplify a little bit before we go ahead. See anything we can factor?
Like the second set brackets, factor of the set, like column factor of 6.
Perfect. Yes.
6.
Perfect. Thank you. Yeah, actually, I'll tell you what. I'm going to leave the x in. You're right, Luke. You could take an x out. But I'm going to leave it in so that I've only got 2 functions to multiply together, and I can use my constant rule. Perfect. Okay, so we're just going to redo this as, what's 6 times 7? Is that 42?
6 times 7
Yeah.
42.
Or
6 times 6 is 36.
Yeah, I guess. Sometimes I'm 400. That makes sense.
Okay. And the nice thing, if you remember, I think there was like this is the constant rule. We can just leave the 42 alone. And we're just going to do the product rule on this stuff here.
What is the exponent 6?
Oh, yeah, the exponent 6.
That needs to be in there, apparently.
You're supposed to leave it invisible for a little while. RJ, you should be a man and go.
That's not.
No,
Alright, yeah.
So,
got it. Hey, what rule? So, yeah, we're going to use the product rule on this, and there's a constant in the front. We're just going to, we can just not worry about the constant for now. We can keep it there. Okay, so, remember the product rule? Luke, do you remember it?
Derivative of the first times second times derivative of second times first.
Almost right. It's just like plus the second times derivative of the first. Good.
Oh, okay, yeah.
Yeah. And I always do it the other way around. So derivative of the first, so 6 times 4x cubed plus 3x squared to the exponent 5. Now we have to do the derivative of the inside. 12x squared plus 6x. Oh man, that is really terrible. Derivative of the first times the second. Wow. I'm gonna run out of board.
I'm running out of paper.
Plus the first, okay, we can just do the first. 4x cubed plus 3x squared, the exponent 6. Times the derivative of the second. 4x plus 1. And this whole entire thing is still being multiplied by that constant.
It's pretty cool.
Okay, so that's the second derivative, unsimplified. And we can factor a whole bunch of things out of this. Okay, so we can actually factor out 4x cubed plus 3x squared to the exponent of 5 out of both of these.
So that was 6, not 6.
Yeah, so that's going to leave us with one of these binomial terms. So it's going to be left here,
Okay.
but we're going to be able to factor it out of that. And I think we could also factor out, oh, look at this. We can factor, no, we can't factor that out. All right, so let's do that. (42) times 4x cubed plus 3x. Oh, this is just getting too full. Better put my 6 in here.
Missing bracket.
I'm missing a bracket. An unpaired bracket. It's like doing JavaScript all over again. There we go. Wow. You'd make a great compiler.
Me? Why?
Because you'd say unpaired parentheses on line 42.
No, I was just watching. Like, you're gonna miss
Parentheses bother you.
Yeah.
You were watching saying he's going to miss it.
Yeah, because you always do. Every time.
You have to say it like that? Wow, you always do. All right. Anyways, that might make it a little simpler to simplify. It might not. That's it. That's higher order derivatives for now. And all you do is take the derivative and then you take the derivative again. So that's it. Is there anything else, Luke?
No, that's good.
Okay. Well, thanks for coming to our video conference.
Yeah.
And we'll be here like if you got a question, yeah. Just video call me. It'd be fun.
All right. Sounds good.
Okay. Thanks a lot, Luke.
Yeah, thanks, Travis. See ya.
We'll see you.
Oh, it's just you and me.
Okay.
Hmm.